Okay, now for a very important definition. The absolute value of a complex number is nothing but the length of its arrow. Yeah, by the Pythagorean theorem, the length of this arrow is a squared plus b squared and then the square root. So you should be familiar with that from three-dimensional geometry or two-dimensional geometry. The name absolute value, I suppose, comes from this observation. If I take z to be a real number, then the absolute value is by definition a squared plus 0 squared, so the square root of a squared. And this is the absolute value of a, the real absolute value. Yeah, because here a might be negative, so I have to put the absolute value because the square root cannot be negative. So this is a special case, or this is the general definition in the complex numbers in R2, and the special case is the real absolute value. That's, I think, why this here is also called the absolute value of the complex number. So here, this length is this number. So here we have an almost trivial consequence of this definition, but the importance of this little formula cannot be overstated. So this turns the absolute value, which is a square root of some sum, into a product. And this is proof-wise often very useful and very handy if I can transform this into this product. Okay, proof here, as I already said, almost trivial. So the absolute value squared is here this square root squared, which is a squared plus b squared, which is nothing but c times z bar by proposition 9.3. Now if z is any complex number that is not equal to 0, then I can divide here by z and by the absolute value squared, because this is not 0. And I get this useful formula. 1 over z is the complex conjugate divided by the absolute value squared. And this here is much easier to remember than this formula that we derived in the last video. So you should note that the inverse of a complex number not 0 is its conjugate divided by the absolute value squared. So if I want to take the inverse of this number, I need the absolute value, which is the square root of 3 squared plus 4 squared, which is the square root of 25, so 5. So by this formula, the inverse is the complex conjugate, 3 minus 4i divided by the absolute value squared, which is 25. And then I can split it up in the real part. This is 3 divided by 25 minus the imaginary part, 4 over 25 times I, which is 0.12. Just multiply by 4 the numerator and denominator, minus 0.16 I. And you should check that the product of these two numbers actually is 1. So to conclude this video, a very important proposition. First of all, the absolute value is positive for every complex number that is not 0, and here conjugate and number have the same absolute value. This is trivial. Okay, by definition, this square root is bigger than 0 if at least a or b are not 0. And here this is also trivial, because if I plug in the minus b instead of b, then because of squaring it, the minus gets lost. Or you could use geometry. Z and Z bar have, of course, the same length because they are mirror images of each other. Then the absolute value is multiplicative. This is not totally trivial, but very, very useful in proofs. And one of the most important inequalities that every analyst uses 3 times a day is the triangle inequality. We already used this for real numbers, but there it wasn't apparent what this should have to do with a triangle. Now in the complex numbers, this is clear because if this is the number z and this is the number w, or the associated arrows, then the sum of the two is this arrow by the parallelogram rule. And now here we have a triangle, and this simply states that this side of the triangle cannot be longer than the sum of these two sides, which geometrically, of course, is obvious. But we're going to prove this rigorously using the definition of absolute value. Okay, for the proof, number 1 is really trivial. I didn't like this word when my math professor put it on the blackboard because often it was trivial to him, but not to us students, not at all. But in this case, this is not worth the chalk. Now here, there's a first application of this very useful identity, which is very elegant, I think. We're not proving this, but we are squaring it. So here we're using this identity, but not for z, but for z times w, which also is a complex number. Okay, this is simply that for z times w. Now we're using that the conjugation is multiplicative, so this here is the same as z bar times w bar. Now complex multiplication is commutative, so I can interchange in any way that I wish. And now again, by this useful little identity, here we have the absolute value of z squared times the absolute value of w squared. But this, of course, is, if I take the square root, this proves this equation because both sides here are non-negative. If one of them could be negative, then I would have to make a distinction, but here I get this. You should make little notes writing down what I just said, because this is not obvious, only if here those are non-negative numbers. So maybe like that. Now the proof of the triangle inequality is a very nice application of almost everything that we've learned so far. Using the same trick as before. I do not prove it for the absolute value, but for the absolute value squared, because again, then I can use this sneaky little identity. So I have this. Now conjugation is additive, meaning this here is the same as this. And now using distributivity, I get z times z bar plus here, very good. This is absolute value of z squared. This is absolute value of w squared. So here we have these two. Here I interchanged the order. And now comes a very mean little trick. W is the same as w bar bar, because obviously conjugating twice leaves the number the same, because I reflect on the real axis and reflect again, so I end up with the same number. But now this here is the same as this, using the hard to pronounce multiplicativity of the conjugation. And now here, I hope you can still see it, we have this. So this here is nothing but 2 times the real part of this guy, z times w bar. Now we're almost finished, because the real part of any complex number cannot be larger than the number itself. Okay, so here the real part is less or equal to the length of the whole arrow. That's what I'm using here. Now, by multiplicativity of the absolute value, I can write it like that. And of course here w bar has the same absolute value as w. And now, isn't this wonderful? We have, by the second binomial formula, this here. And now all I have to do is to take the square root and, important, observe that the square root is a monotonely increasing function, so it respects here this less than or equal to, and then I get the triangle inequality, that the absolute value of this is less than or equal to the sum of the absolute values. Okay, there's nothing more to add. This is just wonderful, a wonderful application of all the notions and things and of course mean tricks that we have learned so far. For this here, this is very, very ingenious. Although it's easy, I wouldn't have thought of it like in 100 years. All right, so much for the absolute value and complex conjugation. Hope to see you soon. Hope you enjoyed the video. Thanks for watching.